Now, in the last class, I was not able to open this presentation. So we discussed few cases of recursion, and we discussed Tower of Hanoi and how it falls into the case of recursion. So we saw that if you try finding Hn, it actually is the one replacement of a big disk from pole A to B, and then twice you are going to replace the n-1 disks, one from A to C and the next from C to B. So we discuss in terms of Tower of Hanoi, and that gives us something called as recursive relation. So whenever the value of n depends upon the previous value, which is n-1, then we call that equation as a recursion equation. And that is actually one criteria of looking at a recursive equation, or when we want to implement recursion. So if we see that there is a repetitive pattern, and when the nth value depends upon n-1 value, then we are going to use recursion. And in the last class, we saw some examples. So today we are going to see the implementation of those examples. So we saw that factorial is a very good example of that, and they have implemented it here. Again, we saw that n factorial is equal to n multiplied by n-1 multiplied by n-2 up to 1. So this part n-1 multiplied by n-2 multiplied by n-3 up to 1, this is nothing but n-1 factorial, and we saw that we can also represent it as n-2 factorial. So here, if you look at the compute factorial program, you will see that they have imported the scanner class to take input, and we are taking that non-negative integer to calculate factorial. Now that integer, whatever value, it is by default a string value, so we are converting it into integer value and storing it as n. Now when we are calculating the factorial, we are calling the function factorial n. Now, so whatever factorial n returns, that will be printed here. And if you look at the factorial n, so here you will notice that instead of integer, we are using long here, because the factorial value for a very small value also, you will get a large output. And in order to make sure that it doesn't go beyond our integer range, they have used long type, and we are passing the integer value. Now, if it is n, if we entered 0, then the factorial is 1. Otherwise, so this is our base case. And if it is something more than 0, then every time we are going to return n multiplied by factorial n-1. So you call n-1, again, it will go through this and it will multiply n-1 multiplied by factorial of n-2. And assuming that this factorial of n-1 is going to give us the factorial of n-1 by calling the same function again. So if you, the live example, if you execute this, you will see that I think the default value here is 9. So they have entered 9, and this value of factorial 9 we get is 3628. Let's go back to the presentation. So we know that for our base case here, we assume that 0 factorial is 1. And then after that, 1 factorial is 1. 2 factorial is 2 multiplied by 1, 2. 3 factorial is equal to 3 multiplied by 2 multiplied by 1, which is 6. 4 factorial is 4 divided by 3, 1, and so on. So here they have shown a sample execution of how if the function calls itself, then what will happen if we give the input value as 4. So if you enter the value 4 as a n, then It will be when we call the factorial function, it will be interpreted as 4 multiplied by factorial of 3, because n multiplied by factorial of n minus 1. Now again, this factorial 3, it is going to call itself, and we are going to evaluate it as 3 multiplied by factorial of 2. Then factorial 2 will be 2 multiplied by factorial 1. Factorial 1 will be 1 multiplied by factorial 0. Now we have reached the base case. So factorial 0 will return us 1. So now we can calculate 1 multiplied by 1 first, and it is going to return the value 1. Then we are going to calculate 2 multiplied by 1, which will return the value 2. And now it will calculate the factorial 4. 4 multiplied by 3 multiplied by 2, which is 20. So this is a returning sequence. So it is going to return 6. And now you calculate 24. So in the execution, whenever we call function by giving value 4, it returns 4 multiplied by factorial of 3. So right now we don't know the value. Unless we reach to the base case, recursion will only start giving us value when we reach the base case. So on the stack, you will see that we are storing the return addresses of all methods. And we have to also give the some space allocated for each method to execute. So we started with the main method. So here is our main method in the beginning on the stack. Then when we call factorial 4, here is the space allocated for factorial 4. So first allocated for main. Now factorial 4 is calling factorial 3. So whatever space is needed to calculate 3. And when we are done calculating factorial of 3, we can substitute the value here and return the value 4 multiplied by factorial 3. But when we call factorial 3, it gives us value 3 multiplied by factorial 2. So again, one more line or more space is allocated to calculate factorial of 2. Then it calls 2 multiplied by factorial of 1. And you will see that in stack, first for main, then for 4, factorial 3, factorial 2, factorial 1. Now factorial 1 we call 1 multiplied by factorial 0. So that much space is getting, memory is getting kept aside for factorial 0. Now factorial 0, it executes, it is a base case, so it returns the value 1. So now we have value 1. So we can now calculate 1 multiplied by 1, and that will give us the value 1. Now this 1 is returned, and after it is returned, we don't have to store or we don't have to keep aside any memory on the stack. So that space will be emptied. So now you will see that once it returns 1, you no longer have space allocated for factorial 0 because we calculated it and returned the value. Now, after 1 is returned, we calculated factorial 1, and that factorial 1 value is returned for factorial 2. So now this value is 1. So 2 multiplied by 1 is 2. So now we can return that value to factorial. So after returning that value to factorial 2, now we can calculate factorial 3. 3 multiplied by 2, 6. So again, we no longer need to store space on the stack for factorial 2. So that space is gone. So the value of factorial 3, 6 is returned now to factorial 3, and we calculate 4 multiplied by factorial 3, which is 64. So that value will be returned to factorial 4, and we no longer need space required for factorial 4. So now in the end, you will see that whatever value, we will return that factorial 4 value to the main function, and then the space we no longer require. So the way the space is allocated initially for factorial 4, then for 4 and 3, 4, 3 and 2, 4, 3, 2, 1, 4, 3, 2, 1, 0. Then once we know the value of 0, which is the base case, here in this case 1, so we no longer need this space, so that is gone. Then when we calculate, after getting value 1, we calculate 2 multiplied by 1 is equal to 2. So we no longer need this space. Now we have 2 multiplied by 3. We calculate factorial of 3. So we no longer need this space and so on. Now similar example is if we are calculating summation of n numbers. So we can exactly implement it in a similar fashion, but now instead of multiplication, we are going to have addition, and our base case might be summation is 0, so till it reaches to 0. From n to 0, we are going to keep adding the numbers. Now another similar problem is now summation exactly same fashion we can implement it, but instead of multiplication, it will be summation. Now another problem which is generally asked about recursion is Fibonacci series. And if you look at the Fibonacci series, the first two numbers are given to us. So it needs first two numbers, because in Fibonacci series, the third number is calculated as summation of first and second number. So Fibonacci of index is index minus 1 plus index minus 2. So in other words, we can also say Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. And starting points are given as, because if we don't know this n minus 1, what is Fibonacci of n minus 1 and n minus 2, we cannot calculate Fibonacci of n. So at least we need to be given two initial conditions which to start calculating the series. So we must have these two conditions given to us. So now we know Fibonacci of 0 is 0 and 1 is 1. So that will be our starting point. So now we can calculate Fibonacci of 2 is equal to Fibonacci of 1 plus Fibonacci of 0, which is 1 is given to us 1, 0 is 0, so that will be 1. Now we know 2, so we can calculate 3. We can say now Fibonacci of 3 is equal to Fibonacci of 2 plus Fibonacci of 1. So 2 we just calculated, plus Fibonacci of 1 is 1, 2. And in the similar fashion, if we go on calculating, so this is 0, 1, 2, 3, 4, 5, and so on. So we can calculate the Fibonacci by using recursion. So here you can see that it is calling the function itself by giving one value less, two values less than my original n, then that should give me the Fibonacci of n. So here, if we are solving Fibonacci of 3, how will it solve? So Fibonacci of 3 is Fibonacci of 2 plus 1. Now 2, what is Fibonacci of 2? It is 1 plus 0. So if we break it down as Fibonacci of 0 plus 1, that is the value of Fibonacci 2. And this 1 as it is. Now we have reached at a point where we have three base cases, and we are going to substitute the values of Fibonacci. 1 is 1, 0 is 0, and 1 is again 1. So that will be 1 plus 0 plus Fibonacci of 1. So this is 2. So let's see the implementation using recursion. So again, we are asking the user to enter. So this is the scanner class we have to include. And in the main class, we are taking the n for which index we want to go. So we know that if we want to find the Fibonacci for index 7, first two are already given. So next 5 we have to calculate, or first two we already know. For 0, it is 0, and for 1, it is 1. So the remaining 5 we will calculate. And at index, so here Here we have to calculate for a particular index Fibonacci of n. So we are not giving the series here. So Fibonacci number at particular index is we are passing that index to the Fibonacci function. And again, this is a long function. So here you will see that if somebody enters the base case as 0, we are going to give return 0. If the base case is 1, we are going to return 1. So those are the two base cases we had. If the number is greater than these two base cases, then we are going to return that add Fibonacci of index minus 1 to add index minus 2. So just the same thing we did it. So we are calling the same function twice, once to calculate index minus 1, once to calculate index minus 2. And every time it is going to calculate till it reaches to the base case. So you can see that by recursion, the code becomes smaller. So you will see that most of the iterations that we did it was with for loops. So you can either use iteration. So every problem that we are solving with recursion, we can also solve it with for loop and vice versa. And every problem in iteration, we can convert it as a recursion problem. But that's not the point. The point is to find out which is the better solution at any given time. So some problems, it is very obvious that if we calculate n minus 1 and add something to this or multiply something to this, we are going to get value of n. So those kind of problems, we are going to use recursion. And some problems, you will see that it is easy to just use a simple for loop. And so in that case, we are going to take iteration approach. So for example, if we have to print, let's say, if we have to print first 5 numbers. So in that case, we know that if we just use a for loop. So let's say if we can convert it into a recursive. So every problem iterative is by using any loops we saw. So it might be do while, it might be while loop. But whenever we can use a loop and do a repetitive task, we call it as an iteration problem. So here takes a little bit time to appear. Okay. So iteration and so in iteration, let's say if you want to print numbers 1 to 5. So we can say simply for I is equal to 1, let's say I less than equal to 5, I plus plus, and you are going to say now system.out.print. I'm just going to write print system.out.print maybe, and you can here say %i, right? Or you can say print ln, which will print it on a new line. So if you use this simple for loop on the output, first it will print 1, then 2, then 3, then 4, then 5. So something similar, how can we do it with a recursion? So let's say we are going to have a function print up to n. And in that case, we can pass value to that n. So it will increment the value. So it will first print, let's say, print I. So it will print the value, print ln %i. Now after printing the value, it will increment the value of I, and it will call the same function again. Right? So if we do that recursively, it will print 5 values. So maybe 5 is our end case. So here we want to check maybe if I is not equal to 5, then you do this. Then you print and include and then call the same function again. So same thing, but here you will see that writing the for loop is easier than recursion. So maybe we will use the iteration. In factorial, you will see that writing the recursion is simpler because it was very, every time you will see that if 5 factorial can be broken down as 5 multiplied by 4 factorial. So their recursion is more, you can say, obvious to use. So we'll see now the execution of Fibonacci series, how it will. So I think they didn't show here how it is going to happen like in the previous case. But when you call Fibonacci of 4, it is going to return you Fibonacci of 3 plus 2. See, I can make it bigger. So we can break it down as Fibonacci of 3 plus Fibonacci of 2. Now, when we call Fibonacci 3, it is going to give us Fibonacci of 2 plus 1. Then Fibonacci of 2 is going to give us 1 plus 0. Fibonacci 1, we already have the value as a base case. So when we come at a point where all are the base cases, that time it returns the actual value. So for Fibonacci 0, it will return 0. So if you call Fibonacci 0, the return value will be 0. If you call Fibonacci 1, the return value will be 1. Now you have 0 and 1, you can add and return the value 2, Fibonacci 2. Similarly, for Fibonacci 1, if you call Fibonacci 1, it's going to return you 1. So now you can have value of both 2 and 1, which is 2 plus 1. And that value 3, we are going to pass at Fibonacci 3. Now, when the second term, Fibonacci 2, again, we are going to call Fibonacci 2, which is going to give us 1 plus 0. 1, we are going to call, and that is a base case, so it is going to return the value 1. 0, we are going to call, and Fibonacci 0, it is going to check. This is the base case, so return value 0. Now this is going to calculate 1 plus 0, and it is going to return 1 as value for Fibonacci 2. And for 3, we got 1 plus 1, we got value 2 here. We have both the values, it will calculate 2 plus 1, and we finally get value 3. So that is the value at index 4, 0, 1, 2, 3, 4, and so on. So every time you will see that those many stack entries and those many calls will happen. So if I have to calculate Fibonacci 4, how many times we are calling that function? 1, 2, 3, 4, 5, 6, 7, 8. 8 times we are calling that function to get a value of Fibonacci. So when we are implementing recursion, we will see that always we will break it down into three different things. So first thing is, what is my base case? At what point we are going to stop this recursion? Then we are going to call the recursion, and we are going to also call the pre-n minus 1. And the third case is, so this is my stopping point, and then we are going to return the whatever value we are calculating. So it can have more base cases, like in case of Fibonacci, we had 2 base cases. So if it is 0, it is 0. If it is 1, it is 1. If it is more than 1, then we are calculating it with previous 2 values. So you might have more base cases which are used to stop the recursion. And every recursive call should reduce the original problem to a smaller sub-problem. So it breaks it down into n multiplied by n minus 1 in case of factorial. In case of Fibonacci, it breaks it down into 2 subproblems, n minus 1 and n minus 2. So here is another program which they have implemented using recursion. So this is a program which is asking us to print welcome n number of times. So again, in iterative approach, what will we do? We will just write a for loop which goes from 1 to n, and those many times it will print hello, or sorry, welcome. Now here since we want to use recursion even for this problem, we are going to see how we can break it down. Can you see how can you break it down, this problem? So printing welcome n number of times. So yes, can anybody tell me how can we break it down? So for factorial, what we did is n multiplied by, calculate the factorial of n minus 1. So if we just want to print the welcome message for n number of times, with iterative approach, it is very, very easy. If you want to force only recursive approach in this case, how are we going to implement with the recursive approach, not iterative. So we created one function and it takes two attributes. What do you want to print and how many times you want to print? So welcome is the string to be printed, n is number of times to be printed. So this is the function, recursive function that we want to create. Now, how will we reduce the problem? So at every step, the problem should get reduced. So when we call factorial 5, we are doing 5 multiplied by factorial 4. So the problem gets reduced a little bit. So here, if we are printing n times, if I print once, then my problem size is going to get reduced. And now I have to print n minus 1 times. So here, we are going to print the message once. And next time, we are going to pass for the same function, we are going to now pass n minus 1. So now it will again go print reduce, again go print reduce, up till what? So we need to have a base case till n reaches to 1. So as soon as n reaches to 1, we are going to print, and here when we reduce it to 0, then it will stop. Okay. So this is kind of simple recursion. So in this case, again, recursion is not the best approach, but just to show you that every iterative problem can be solved using recursion. So we are writing one string and number of times it needs to be printed. So here the base case will be when it reaches to 0, we are going to stop. And that condition we are checking here. So before printing, we are going to check is n greater than at least 1, then print reduce n. If it becomes 0, then obviously it will not go in the if loop and it will stop. Straightforward. Now another problem they have talked using recursion is checking if a string is palindrome. So what is palindrome? You know, a string, if you read it from both sides, it should read the same. So for example, let's say if you take a string ABC, then ABC, if you read from this side, it is ABC, from this side, it is CBA. So ABC is not equal to CBA. So this string is not valid. But if you take a string ABA, then if you read from this side and read from this side, from both sides, it is same. So this problem they have now. If you're implementing it using string, there are various simpler approaches. So we can directly reverse the string and check if this string and the reversed string is same, and then we can say it is palindrome. But if you are using recursion, then again you have to reduce the problem size. So now, if you have let's say this kind of a string A, B, C, D, and you have to use recursion in this case, then how will we reduce the problem to n minus 1? So what they are doing is first they are checking A with A. So if it matches, then we are going to reduce the problem size. Now, how will we reduce the problem size? So considering that I checked the number at index 0 and n-1, and this character matches. Now I have to move forward in my string. So forward from one direction and backward from one direction. So next, which character will I check? So next you will check B with B. And for that, I have to move the indices. So instead of now 0 to n-1, my indices should go to 1 to n-2. And we are going to check that. So now the problem becomes, we are calling the same problem of checking 0 n-1. Now we are going to check 1 n-2. If that matches, so recursively we are reducing the problem size and calling the same function is palindrome. So here you can say if the length of the character is only 1, then it is palindrome, right? If I give any string, let's say S, then you read from this side or this side, it is still same string. So if it is a single character, it is always going to be a palindrome. So we are going to is palindrome. So it is going to return true or false. If the string is palindrome, it is going to return true. If not, it is going to return false. So if the length is 1, it is every character is a palindrome in itself. Now, else we are going to check that character at 0 is, if it is not same as character at n-1, then you return false. Otherwise, we are going to continue checking. So otherwise, it means A and A matches, so you continue. So you call the same function again. But now for a substring, which starts from 1 to whatever was the previous length of the string, -1. So now we are going to pass the index 1 and n-1, and it is going to check again, does it matches? Yes. So again, it is going to call is palindrome, and this time we have only single character C. So if the length is 1, it is true. So the whole palindrome function returns us true value. So just one example of. Now they have another way to look at it also. So what they are doing it is public static, again Boolean, and is palindrome, it is a string. So return whatever value your is palindrome function is giving, where we are passing a string and my first index, which is 0, and last index, which is s dot length -1. Now if high is less than or equal to low, so we don't have now many characters left and maybe just a single character left in between, then you return true. Or if as long as we have some characters here and here to be checked, we are going to check if it is whatever the lower index value is same as higher index value, and we are going to keep updating the low and high by increasing one value to the lowest index, which was 0, and decreasing 1 from the length -1, just like in the previous case. So just a different way of implementing. So here next we checked at index 1 and index n-2. Same thing, they are doing it by reducing it by 1, the low by 1, increasing the low by 1 and reducing the high by. So that will take our pointers to now B and. Then here is example of binary search. So maybe we will do it in the next class.